we are going to end off this unit of electricity and circuits by talking about batteries. We've been using batteries throughout this unit as our power supply, our power source, but we haven't really talked about what's going on inside that battery. So, batteries can be split up into two different categories. We've got primary cells and secondary cells. Primary cells are essentially these one-time use batteries. That chemical energy that's stored in that battery can only be used once. Most batteries that we've experienced kind of plugging in toys or remote controls are these one-time use disposable batteries. Typically, we see them in AA, AAA, C, D. All of those have a nominal voltage of about 1.5 volts. They are not rechargeable. They only can be used once. Secondary cells are batteries that can be recharged. We'll talk about some of the process to do that, but a lot of batteries in your everyday lives are these secondary cells. For a long time, secondary cells, these rechargeable batteries, were thought of as these AA's that you could plug into a little thing, hook it up to a socket, and it would recharge that battery so you could use it again. But nowadays, the most common rechargeable batteries that you're using are in your cell phone, in the iPad, and a laptop. All of these are rechargeable, that when you plug it in at night, it is recharging the battery that's inside. Most commonly, these are lithium batteries in a silver flat pack, offering almost 7 volts of voltage there, but it is rechargeable. Another commonly used rechargeable battery is your car battery. Your car is recharging that battery as it drives so that you are able to start your car when you're ready to start it at the beginning. It's able to power that ignition as well as the lights or your radio, even if the car isn't running. So this process of recharging is kind of an interesting one. So some of these batteries, if they're a secondary cell, can reverse the chemical reaction that takes place to create that potential difference. So say I have a cell here that creates a current flowing around, leaving the positive into the negative as our conventional current, the direction of the positive charges flowing. Well, to recharge that circuit, basically, or recharge that battery, basically what you're doing is you're connecting it to a circuit of some external voltage that pushes current in the opposite direction. So here current is flowing from left to right. If we push current in the opposite direction, it starts to resort some of those charges and creates this recharging effect that it's then storing up that electricity energy in the form of a chemical energy again, that it can be reused and recharged in this fashion. So again, that is a secondary cell that is allowing us to do that. Inside the battery, there's more going on than the simplistic sense that we've been looking at so far. So far we've been just saying a battery provides voltage. Well, there's a little bit more going on. Inside that battery, there are two main parts. There is this supply of energy, but there's also this internal resistance that battery offers. We're going to talk about those two different categories here in this video. This first one we call the electromotive force. It's not really a force, it's more of an energy that is being transferred per unit charge that's in there. The symbol that we're using here is a Greek letter epsilon. It looks like a little curly E. And our unit for that is the same as our unit for voltage. The unit is in volts. That's the amount of electrical energy that we are going to be passing through there. Internal resistance here is represented by this lowercase r in units of ohms, just like we saw with resistance in previous parts of our unit. Let's look at what this looks like in action. So the way I would draw a battery if I wanted to show the internal components of it is this dotted line rectangle with inside this EMF, electromotive force, and some sort of internal resistance. Well, here I have defined the internal resistance, and I've defined what's going on in the circuit externally. I want to work backwards to figure out what that EMF, what is that epsilon value there inside the battery. Well, I see that I have a current, and I've got 3 different resistors here. So I'm going to just, in this first case, just ignore this box. And just imagine that that resistor is a resistor like any other. I can find the total resistance is just connected in series 7 plus 3 plus 0.5. That's 10.5 ohms of total resistance. If that's the total resistance and this is the total current flowing through, I can find this voltage essentially is just I times RT, the current times that total resistance, 1.2 times 10.5. That's just like how we calculated voltage before. Here I'm just ignoring the fact that it's called epsilon. It is measured in volts, so I'm just going to calculate it like voltage. That gives me a EMF value of 12.6 volts. So again, I solved that just like a simple series circuit with 3 resistors. 7 plus 3 plus 0.5 gives me 10.5, which can then calculate 12.6 volts. This shows up in the IB Physics data booklet as this equation here. This equation is essentially the same thing as V is equal to I times R. Instead of V, it's showing epsilon, which is the EMF, the internal energy of the battery. And then instead of R, it's showing R plus R. So big R is the external resistance, and little r is the internal resistance. If we look at that example again, big R is this 7 ohms and 3 ohms. So total big R is 10, and little r is 0.5. So all we did here is I times big R plus little r. We just did that part first. So it's the same equation. You can use whatever you're most comfortable with. So looking at this example now, saying that, okay, that internal energy, EMF, was 12.6 volts. That isn't what we're actually measuring in the battery. We're not able to really get at that internal energy because this internal resistance is changing it by the time it makes it to the terminals of the battery, the 2 parts that we're hooking up our circuit to. So let's imagine that we can't see what's inside that. All we can actually see is what's outside the battery here. So this 1.2 amps and this 7 and 3 ohm resistors. Well, the voltage that's dissipated by this 7 ohm resistor is just I times R, 8.4 volts. The voltage dissipated by this 3 ohm resistor is 1.2 times 3, or 3.6 volts. This is all the voltage that circuit is using. So if I add that together, I can find what the total voltage is here. That's 12 volts. So this battery is supplying to the circuit 12 volts of voltage. But if we look back inside, that EMF value was 12.6 volts. 0.6 volts is being used up or dissipated by this internal resistance. So not all of the voltage makes it to the terminal voltage. So that gives us 2 pieces here. This epsilon EMF is 12.6, but V, the voltage of our circuit, the terminal voltage, is 12. We're not able to get quite all of the energy out of that. So if we want to take that EMF value and then to work backwards and figure out what R is, we can do that too. If we know what EMF is, and we know our external resistance, we know the current, we can use that equation to find our unknown. In this case, our unknown is R. That's our internal resistance. Plugging in what we know 9 is the EMF, 3 is the current, 2.5 is the external resistance. All that's left is R, the internal resistance. We can solve for that. It ends up being 0.5. So not too hard to get to that if you know all of the other pieces. Where this gets a little bit more interesting and a little bit more of a walk to get there is how we can graph this to actually experimentally figure out from a battery what's going on inside. Because you can't just cut it up and see what it looks like inside. Well, you could, but it wouldn't read out an EMF or an internal resistance. Instead, it would just look like the inside of a battery. Well, here, if I take this equation, this is the equation that's in the IB Physics data booklet, and I expand it a little bit, multiply, distribute that I, that current to both. So we have E is equal to I times big R plus I times little r. Well, this I times big R, we've seen that before. That's Ohm's law. Ohm's law is voltage is equal to I times R. So instead of IR, I'm just going to plug in voltage. Now this is the terminal voltage that we saw of the battery. That was the 12 volts. EMF, was at 12.6. That's that internal electromotive force. Now I can rearrange that to solve for V. That terminal voltage is equal to epsilon minus I times little r. And I can graph, by taking a variable resistor, I can graph how the current of the circuit changes as the voltage measured in that circuit changes. So if I increase the current, the voltage that's happening there is going down. Basically, to increase the current, I have to decrease the resistor, the external resistor in that, and I get a shape that looks something like this on this graph. Well, a graph that's linear like this has an equation in the form of y equals mx plus b. I can rearrange this writing of my battery equation to fit that form. And it looks something like this, that y is voltage. M, our slope, is the opposite, so minus whatever the internal resistance is. X is my I, so that's the x-axis. And then B, my y-intercept, becomes EMF. So if we graph out some different examples here in a circuit that includes a battery with internal resistance, we can actually figure out from the slope and the y-intercept what that epsilon EMF value is, as well as the internal resistance. And that is a lab that we'll be doing in this class. So takeaways here: you should be able to describe the difference between primary and secondary cells. You should be able to define the electromotive force and describe how it is different than the battery's terminal voltage. You should be able to solve for a circuit that includes a battery with internal resistance. And then this cuts off. You should be able to describe how to graph this and then use that graph to figure out what the internal resistance and EMF values are for that battery.